Hello, my name is Patricio Whittingslow, and welcome to my talk, An Operating System in Go. Corporate disclaimer, all views and opinions are my own. So, if you've been following my talks at GopherCon, you might have come across the fact that I am a counterculture sort of gopher. Even among the Go community, I've used Go where gophers warned me not to go. Like writing this 3D design library last year, little shout out there. So it's no surprise that this year is no different. Does anyone know what this is? Show of hands. All right, yeah. Goos is a Go environment variable, and that is how it's pronounced. It tells the compiler what kind of operating system the Go program will run on, the one being compiled. Why do we need to tell the compiler what OS our program runs on? Ever wonder? Here we have a dial TCP call. This is the function that is called every time you want to connect to a TCP client server, whenever you receive a HTTP request or send one out. Sorry, when you send one out. If we work our way down, we'll eventually arrive at this function, internet socket, which itself has a socket call. Keep working our way down. And we have that the socket calls out to a function called raw syscall. The raw syscall function calls syscall6. And this is several layers in deep. I've skipped a couple layers. And this is where our mental model of Go might break down. I mean, this function doesn't contain any, it doesn't have a body, no Go code, right? But we can click on it, go to definition, and we'll come across this. Syscall6, ABI internal, SB, no split, $0. This is Go assembly. And you don't need to understand assembly to get the gist. It's just enough to know that there are just a few lines in this function, really. It's short, sweet, some would say. And there is a curious instruction, though. The syscall instruction, right there in the middle of it. You see, this instruction is actually a function call to a function that is provided by the operating system, in this case, Linux. Have we got any Linux nerds in here? Who knows what this actually does? Oh, I saw a couple hands go up. All right, so if you raise your hand like Ron just did, you know I'm running a Linux E590. I'm running a ThinkPad. E590 is the model. You know it has this driver Wi-Fi chip, which the Linux network kernel will use to send out an ARP, IP, TCP packets to establish that connection that was called with dial TCP. Thing is, you probably didn't know, I'm actually running a Wi-Fi dongle, so that's not what would actually happen. And y'all don't even know what kernel I'm on, I would hope. So you nor I know what is running when I do that dial TCP call. So by now, I imagine you might feel a little like Alice right now, tumbling down the rabbit hole. You have the look of a person who accepts what they see because they are expecting to wake up. You're all here because you know something. It's been there your entire life, in the back of your program, like a splinter. Do you want to know what it is? The operating system is everywhere. It's all around our programs, even now in this very presentation. It's there when you boot your computer, when you start a Go routine, when you heap allocate, when you connect to a TCP server, it is the world that's been pulled over our eyes to blind you from the truth. The truth being, you don't need an operating system. For some tasks. In a world where goose is noose, there's this proposal Andrea Bariziani so kindly set up in the Go issue tracker. It's a proposed change to the Go runtime. Add bare metal support, which eliminates the Go runtime dependency on the operating system. Bare metal means just no operating system. Your program compiles, and it's the only thing that runs on a computer, or CPU, MCU. MCU is microcontroller unit. I'll be saying that a few times. This proposal is not magic. The runtime still needs that which we remove. It's just that now we, the user, have control over what is being provided. Build a Go program such that you know the limits of the hardware used or OS functionality being used. You are in control. This has interesting security implications and can potentially eliminate all C-Go from a Go program, which is why Andrea proposed it. This is the proposed API. So it would let us integrate the Go runtime into any freestanding environment, bare metal or OS supported. For example, a Raspberry Pi Pico. So that little black square you see on it is the microcontroller unit for which we are compiling to. I'll just call it MCU. It's a CPU for all intents and purposes. These variables shown and functions would be linked at compile time by the user when the goose is noose environment is set. So who's currently using Go with no operating system today in this room? I mean, not right now, just historically have used Go with no operating system. All right, Ron, and the usual suspects I see. All right, we, the embedded Gophers, should be very interested in this proposal. In fact, a lot of Gophers have shown support for it, including the Go team. Embedded Gophers is just a term I made up for people who program Go for bare metal targets. It refers, embedded comes from embedded system, by the way. Refers to a computer that's part of a larger mechanical system, such, for example, maybe the flight computer on an Airbus plane, or your smartwatch, in which case you are the larger mechanical system. Last year I gave a talk at GopherCon on this subject, so if that's of interest, go check it out. It's called Go in the Smallest of Places. So, who are these embedded Gophers and what do they do? Andrea Bariziani, the creator of the aforementioned proposal, is the creator of TinyGo. He is an exemplar embedded Gopher. Really neat project, focused on removing C and the operating system from our Go programs. If you remove the OS, who becomes the OS? More to come on that. TinyGo. You all know and love this project. Go, but small. In the smallest of places, dare I say. Whether it be on a small computer or a WebAssembly binary being distributed by a CDN, TinyGo makes you go smaller than ever before with Go. This is the embedded Go project. The embedded Go project just took the Go project and stripped all the OS and C stuff, and they implemented a ARM v7 M Thumb2 compiler. Wild. And there's more. The embedded Go ecosystem is only growing. And there's a common theme among all these projects. No operating system or a heavily stripped down dependence on one. Now, you may think to yourself, why are these guys so dead set on removing the operating system? I myself included, since I work on TinyGo. Do we have something personal against it? Do we not like operating systems? Now, it's not that we don't like them. The word I'm looking for is something along the lines of hate, maybe? I think. No. Operating systems are great when they work. There are reasons to avoid them in development, though. These are just a few. I have not included issues with Linux audio, among several others. So maybe by now your interest is piqued. You look at your OS and you see a problem where you previously didn't see one. But why Go over other well-established languages in the industry? There are academic papers I think I might be interesting to look at that use Go for bare metal. They compare TinyGo, Rust, and C, Rust and C being the next two contenders for this kind of work. This is the TinyJambu paper. This paper benchmarks performance of different languages running the TinyJambu cryptographic algorithm, an NIST finalist, which is like a cryptographic algorithm designed for small devices. And it runs it on the Raspberry Pi Pico, the microcontroller I just showed you. The authors found that the Go executable being generated by TinyGo was 3.5 times smaller than the ones generated by Rust and C. It also found that the performance of TinyGo was 1.5 to 2 times slower. That said, they used algorithms they themselves implemented, translated from C, and do not provide the code as far as I could tell, nor could I find it on GitHub. Sus. Then there's the performance evaluation of MicroPython, Rust, and C, and TinyGo on ESP32. This paper benchmarks languages across several algorithms commonly used in embedded systems. The paper's findings show that TinyGo runs just as fast as C, sometimes faster, sometimes slower. But what was, to me, the most interesting find was that TinyGo programs show no jitter. It means they run in constant time. You look at the table in this paper, and it's just TinyGo shows 0, 0, 0, 0, while other languages show varying levels of difference in a standard deviation of runtime. To explain the jitter differences, the authors note that TinyGo does not run an OS, whereas Rust, C, and MicroPython are all running on FreeRTOS. This is my experience using TinyGo and C is reflected in these numbers. However, after reading this paper, I kept asking the question, what do you mean TinyGo doesn't have an operating system? Well, if we look at FreeRTOS, these are the tasks done by an operating system, right? An embedded operating system, some would say. FreeRTOS does all of these tasks and has been in development for over 20 years and is under stewardship of AWS to continue development. So it's no surprise that TinyGo, being only 7 years old and a community-driven effort, only supports all of these tasks. Do note I'm being unfair to FreeRTOS. It has decades of polish and supports 40 microcontroller architectures. TinyGo only supports 50. Across 150 development boards, jitter-free. Okay, I'll stop. To be truly fair, TinyGo is not feature complete across all those microcontroller units. FreeRTOS does have that polish. But it does get you thinking, right? Why is TinyGo being reported as not having or not being an operating system or lacking one when compared to all of these other operating systems? I mean, supports the tasks and is even more real-time than the free real-time operating system, as we've seen in the paper, well, we can't jump to conclusions so fast. You see, there's one key difference. Let me illustrate. So, that's why we've begun to discuss the possibility of adding OS to the project's name. Starting 30 minutes ago. All right, you're all welcome to participate and just be nice. So that's the rundown. We may or may not have an operating system written in Go already. If TinyGo is not an operating system, I would say it's close to being one. The hardest tasks are in large part already done. Multi-core processing, handling of Go routines on MCUs is working in large part. Thank you, Eike, for the hard work. We also have a brand new user space networking stack working on MCUs and needs testers, El Neto. Thank you, me, and the contributors. We have a wonderful lot of contributors. If you want to help out, talk to me or Ron. And once we have these, will TinyGo finally be an operating system? Truth is, I don't care. My experience has shown me that TinyGo is as fast as C and incredibly lightweight, allowing me to do more than what I'd be able to do with FreeRTOS. I don't have to configure it. It just works right out of the box. I don't have to fight against linker issues, CMake files. I'm able to write Go, a language I praise for being the language for software engineering. And while I've sort of arrived at this conclusion by myself over the years, I was so happy to hear that Cameron, opening keynote yesterday, saying Go is a language about, no, Go is about language design in the service of software engineering. Holy cow. Is that a phrase I believe with every fiber in my body? Thank you, Cameron, for bringing that Rob Pike quote to my attention. So, sorry, FreeRTOS. Maybe someone can explain to me where I'd use FreeRTOS over TinyGo. I'm open to change my mind and give an amending talk next year. And we got to this point in the talk. While I was writing this talk, I began thinking, I've been doing bare metal TinyGo, or bare metal Go, for almost 5 years. I've lived, loved, and laughed TinyGo. Also a couple tears in there. I've carried support for the Raspberry Pi Pico to heights I wouldn't have imagined when I started. My contributions are now part of TinyGo and the Raspberry Pi Pico SDK as well. And I must say one hard truth. I will not always be here. Having turned 30 last year really got me thinking. I must leave the proverbial nuggets of wisdom to the new generation. So, I want to take the opportunity to share some things I wish I knew when I started working on embedded system. And first up, the reuse slice idiom. I found a sort of new way of programming Go, I feel, over the years of working with the Raspberry Pi Pico, where I try to avoid heap allocations. This idiom allows me to work with a buffer of things, and if I need to reuse the object which contains the buffers, I can just reuse the underlying memory by checking the capacity and allocating only if I need to. So if your first reset call is with the largest value of size, you can guarantee you'll never allocate throughout your program. Then there's generational indices. I came across this pattern while developing El Neto, the networking stack. It's useful for when you have several pointers to an object you wish to invalidate all at once when that object is changed or no longer alive, to say. These are an ideal pattern when working with networking stacks or file systems, since if you close a TCP connection, you'll probably want to reuse the memory of that TCP connection, but you'll want to make sure that no other handles to it are like kept alive or validate. So, and also, did you know that you can detect heap allocations with TinyGo using the print alloc flag? If we were to print allocations of the Blinky program, for example, the simplest program you can write in TinyGo, we would arrive at these three allocations. This may be alarming to y'all. If the hello world program of TinyGo allocates, then that is an issue because you don't want to be allocating throughout your program on an MCU. However, if we take a closer look, the first allocation is simply just the make call. It's the basic allocator call. So it's always going to be there. The second one is actually the Go routine stack size. So the Raspberry Pi Pico has a stack size of 8 kilobytes. So that's to be expected. And then there's the last allocation is actually just the task data structure that's associated with the Go routine. So if you're only using one Go routine, we can expect to have at least 3 allocations and only when your program starts. We can filter out allocations using regular expressions. That's the flag you pass into print allocs. I don't know enough about regexp, so I'll just leave it at that. All right, so if you found these wisdoms interesting, you can find more content on my YouTube, specifically the TinyGo code review. I've been reviewing embedded systems packages in the Go ecosystem and sort of commenting code commentary. And you can also join the Gopher Slack and find us at TinyGo or TinyGo Dev. We'll be happy to answer your questions about embedded systems there. So we're reaching the end of the talk. And we started out with dial TCP. You know, we discovered the syscalls that rule the operating system domain. Then we found goos is news. Not because we dislike operating systems, but sometimes the job calls to be closer to the metal. I'm excited about the future, and who knows what can happen. And I'm not entirely sure what the last one there means. Goose is goose, but time will tell. And that's all I have for you today. Thank you.